There's a temperature at which the Earth's surface stops behaving the way it normally behaves. Above 2000 degrees Celsius, ordinary rock becomes liquid. Sand fuses into glass in fractions of a second. Carbon atoms, under sufficient pressure, rearrange themselves into crystal structures that exist almost nowhere in the natural world. The question this archive examines is a simple one. 12,900 years ago, somewhere on Earth, something produced exactly those conditions during the onset of the Younger Dryas, a cosmic event that may have changed everything. And the residue is still in the ground today. What we're going to do in the next 20 minutes is rule out every terrestrial process that could have caused it. Then we're going to look at what remains. The materials in question come from a thin sedimentary layer found at archaeological sites on at least 4 continents. They date to the onset of the Younger Dryas, a sudden global cooling event that triggered the mass extinction of mammoths, mastodons, dire wolves, and giant ground sloth across North America, ending the Bering-Allerud warming period that had brought the world out of the last ice age. The layer sits directly beneath the black mat, the carbon-rich sediment that caps the Pleistocene at 50 Clovis Age sites. Inside this layer, 2 specific materials have been documented that are difficult to explain by any natural Earth process. The first is melt glass. The second is nanodiamonds. Both, by the standard rules of geology and chemistry, should not exist in the quantities and forms in which they've been found. This hypothesis was first proposed by nuclear physicist Richard Firestone and colleagues in 2007, establishing what became known as the Younger Dryas Impact Hypothesis. Their work with the Comet Research Group identified not only the exotic materials but also platinum anomalies in ice core data, geochemical signatures that mirror those found at the famous Chicxulub impact site that ended the dinosaurs. The melt glass was discovered at Abu Huraira, a prehistoric village buried beneath the waters of Lake Assad in northern Syria. A team led by James Kennett and Andrew Moore analyzed samples from the boundary layer and reported their findings in a peer-reviewed paper published in Scientific Reports in 2020. The melt glass at Abu Huraira makes up approximately 1.6% of the sediment by weight. For a thin sedimentary band, this is an extraordinary concentration. When the team analyzed the temperatures required to produce the glass, the numbers ranged from 1720 degrees Celsius at the lower end to over 2200 degrees Celsius at the upper end. To put that in human terms, the melting point of structural steel is around 1400. The melting point of granite is around 1200. The fire required to produce the Abu Huraira melt glass exceeded the melting point of common Earth surface materials by hundreds of degrees. The same team examined quartz grains from the same boundary layer in a 2023 follow-up study. They reported finding shock-fractured quartz, a low-pressure form of shock metamorphism that, based on near-surface atomic airburst experiments, can be produced at pressures under 8 gigapascals. Shocked quartz, when properly identified, is one of the most widely accepted indicators of a cosmic impact event. Its presence at the Younger Dryas boundary, if the identification holds up under independent confirmation, represents one of the strongest pieces of evidence in the impact case. The nanodiamonds were documented earlier and across a wider geographic range. A 2012 paper published in the Proceedings of the National Academy of Sciences described the discovery of 3 different types of nanodiamond at the Younger Dryas boundary in sediment cores from Lake Quetzeo in central Mexico. Among them was lonsdaleite, the hexagonal form of diamond. Lonsdaleite was first identified in 1967 inside fragments of the Canyon Diablo meteorite, the asteroid that created the Barringer crater in Arizona. It's since been documented at multiple confirmed impact sites worldwide, including the massive Popigai impact crater in Russia, where it forms in abundance under extreme shock conditions. The conditions required to form it aren't subtle. Static pressure laboratory synthesis has demonstrated formation above 13 gigapascals and above 1000 degrees Celsius. Shock compression experiments at Lawrence Livermore National Laboratory in 2016 produced lonsdaleite at pressures above 1700,000 atmospheres. These aren't Earth surface conditions. These are the conditions found inside an impact crater. Alongside these materials, researchers have documented magnetic spherules and microspherules across more than 40 Younger Dryas boundary sites, tiny glass beads that form when rock is vaporized and cooled rapidly in flight, another hallmark of cosmic impacts. This is the data. These are the measurements. The question now is what could have produced them. The first candidate is lightning. Lightning is, in raw terms, hotter than the impact case requires. The channel temperature of a typical lightning strike exceeds 30,000 degrees Kelvin. Many times, the temperature recorded in the Abu Huraira melt glass. So on the surface, lightning seems like a reasonable suspect. It isn't. When lightning strikes silica-rich ground, it produces a distinctive structure called a fulgurite. Fulgurites are hollow, branching tubes of fused glass that trace the path of the bolt through the soil. They have a rough, sandy exterior and a smooth, glassy interior. They're usually less than a centimeter in diameter and rarely more than a meter long. The Abu Huraira melt glass shows none of these morphologies. It's found in distributed concentrations across the entire boundary layer of the site, not in isolated branching tubes. More importantly, lightning leaves a magnetic fingerprint. The intense electrical discharge of a strike produces what's called lightning-induced remnant magnetization, a high-intensity, randomly oriented magnetic signal that paleomagnetic analysis can detect in lightning-formed glass. The Abu Huraira melt glass shows none of this signature. Lightning is ruled out by both shape and magnetism. The second candidate is volcanism. Volcanic eruptions produce glass. Most commonly obsidian, a silica-rich material formed when lava cools rapidly. If a volcanic source could be identified, the melt glass at Abu Huraira would have a straightforward terrestrial explanation. This candidate fails for two reasons. The first is location. There's no active volcanism within hundreds of kilometers of Abu Huraira in any direction. The nearest volcanic provinces are in central Anatolia, far to the north, and they weren't erupting at the relevant time. The second reason is chemistry. Volcanic glass typically contains a measurable percentage of water, often between 1 and 7%, locked into its structure during slow cooling beneath the surface. This water content is one of the standard tests volcanologists use to identify obsidian and related volcanic glasses. The Abu Huraira melt glass contains almost no water. Its measured water content is between 2 and 5/100%. This is the same range you find in tektites, the glass droplets ejected from cosmic impacts and cooled in the upper atmosphere before falling back to Earth. Tektites are dry because they cool in seconds, in flight, with no opportunity to absorb atmospheric moisture. Volcanic glass is wet because it cools over hours or days underground. The Abu Huraira melt glass behaves chemically like a tektite, not like an obsidian. Volcanism is ruled out by water content and by geography. The third candidate is fire. Ordinary fire. The kind that destroys villages, the kind that lightning can start in dry grass, the kind that consumed the timber houses of a prehistoric settlement when something went wrong with the hearth. A burning Neolithic village in northern Syria would produce heat. A wildfire racing through the surrounding landscape would produce heat. Could either of those have produced the temperatures recorded in the melt glass? The fourth candidate is industrial. Modern metallurgy can produce temperatures above 2,000 degrees in steel furnaces, glass kilns, and electric arc smelters. If the Abu Huraira melt glass had been found in a layer dated to the last few centuries, an industrial explanation would be the first place to look. But the boundary layer at Abu Huraira has been radiocarbon dated. It corresponds to approximately 12,800 years ago, within the dating uncertainty of the Younger Dryas onset. The Bronze Age hadn't yet begun. The Iron Age was 8,000 years away. The earliest known smelting of metal anywhere on Earth dates to roughly 9,000 years ago. And that was small-scale copperwork at temperatures well below the melt glass range. There were no kilns, no furnaces, no arc smelters, and no industrial chemistry on Earth at the time the melt glass was deposited. Industrial origin is ruled out by chronology. What this leaves is a short list. The terrestrial candidates have been eliminated one by one. Lightning produces the wrong shape and the wrong magnetism. Volcanism produces glass with the wrong water content and isn't located anywhere near the site. Wildfire and structural fire can't physically reach the required temperatures. Industrial activity didn't exist. The set of remaining mechanisms that can produce temperatures above 2000 degrees in distributed concentrations across a sediment layer, dry like a tektite, in association with shock-fractured quartz and nanodiamonds, is small. It contains one item: a cosmic airburst. When a comet or large asteroid fragment enters the atmosphere at orbital velocity, the friction and compression of the air in front of it produces temperatures that aren't measured in thousands of degrees, but in tens of thousands. If the object detonates in the atmosphere before reaching the ground, as the much smaller Tunguska object did over Siberia in 1908, the fireball can deliver radiant and thermal energy to the surface sufficient to flash melt silicate material across a wide area. The water in the resulting glass evaporates because the cooling happens in flight. The shockwave produces the kind of low-pressure quartz fracturing reported at Abu Huraira. And if the bolide is graphite-rich, the transient pressure spike can shock graphite into the hexagonal diamond structure of Lonsdaleite, exactly the polytype documented at Lake Kwitseo. This is the case for the Younger Dryas impact hypothesis as it pertains to the melt glass and nanodiamond evidence. It isn't the case that the impact has been proven. It's the case that the elimination of terrestrial alternatives leaves the impact scenario as the remaining mechanism consistent with the measured data. There are honest objections, and they belong in this archive. The nanodiamond identifications have been disputed in the scientific literature. Multiple peer-reviewed studies have argued that what was reported as Lonsdaleite at Younger Dryas sites is in some cases defective cubic diamond or stacking disordered carbon or misidentified organic material. Critics like Mark Boslow have argued that the evidence falls short of the extraordinary proof required for such an extraordinary claim. A 2016 study published in Scientific Reports demonstrated that Lonsdaleite can be synthesized from glassy carbon under conditions that don't strictly require an impact, which weakens, though doesn't eliminate, its value as a unique impact indicator. The shock-fractured quartz at Abu Huraira, while compelling, hasn't yet been independently confirmed at other Younger Dryas sites, and the absence of a confirmed impact crater dating to 12,900 years ago remains an unresolved problem for the hypothesis as a whole. The 2022 redating of the Hiawatha crater beneath Greenland's ice, once proposed as a candidate, placed its true age at 58 million years, removing it from consideration. What the evidence does establish, with high confidence, is the existence of the boundary layer itself, the extraordinary temperatures recorded in the Abu Huraira melt glass, and the presence of carbonaceous nanomaterials across multiple sites that no ordinary terrestrial process is known to produce in those quantities. The independent researcher Randall Carlson has spent decades documenting the geological signatures of catastrophic events at the end of the last ice age. The channeled scablands, the abrupt sea level rises, the meltwater pulses. The melt glass evidence has emerged as one of the more difficult elements of the case to dismiss. The 2023 Moore paper on shocked quartz, in particular, raised the technical flaw of the impact argument by introducing a piece of evidence that, if confirmed, would be very hard to explain away. What this comes down to is a forensic problem. 12,900 years ago, something on Earth's surface produced temperatures that no ordinary terrestrial process produces. It happened in association with the onset of a 1,000-year cold snap and the mass extinction event that ended the Pleistocene. The materials it left behind: glass cooled in flight, quartz fractured by shock, carbon crystallized at impact pressures. They're still in the ground. The interpretation of those materials is contested in the details. The materials themselves are not. The fire was real. The question of what kindled it is still being argued. This is the archive of the 3,000-degree fire. The dirt is older than every theory written about it, and it's patient enough to wait until we figure out the rest.